Good afternoon, everyone. It's a pleasure to have the chance to introduce this afternoon session during the celebration of the 60th years of anniversary of Centro Protesi. And the session is patient-centered applied research in prosthetics, which is the continuation of the main topic we addressed this morning. From many different perspectives. My role now is to introduce this session, and I would like to start with the simple question. So we are talking about patient-centered research, but what does it mean to have a patient-centered care? So one of the, and the slide, sorry. Vediamo se io le vedo. Vediamo se le mettono online. We have to wait for the in-house presentations to start up, not only the online one. So just a second and it will start. Okay. Okay, you can see on the side, that's fine. Okay. So going back to the start of the presentation was to try to understand this simple question, which is what does it mean to have a patient-centered care? So it might sound simple to have to just simply coordinate all the activities around the patient, but really the first thing we have to do is to listen. And we listen in many different ways. We can listen with our ears, of course. We listen with our hands by the sense of touch. We feel, we listen to the patient with our eyes, and of course through our measurements. And what do we do with this set of information? We basically have to fill in all the boxes highlighted by ICF to better have a description of the patient we are trying to deal with. And why we do that? Because ICF helps us to have a better understanding of the patient needs and try to convert his informal way of expression in answerable clinical questions. So the whole point of ICF is really to make a picture in a way so we can formulate questions that can be clinically answered. And how do we answer? Well, evidence-based practice is giving the methodology to do that, which is through the conscientious, explicit, and judicious use of current best evidences in making decisions about the care of individual patients, which is essentially an intersection of three main aspects, which is experience of the professional, which is the use of evidences, and of course the patient preference. So evidence-based practice is giving us the methodology, and it's not just evidence, it's not just literature, it's a mix of personal, professional experience and patient preference, as we just said. Of course, after elaborating and collecting the required information, we have to apply and we have to audit, we have to double check what we went through our decision on that specific patient. So when do research step in? Well, basically research steps in when we know we don't know, or we understand that we don't know enough. Or in other way, when the outcomes that are important to the patient are moderate or weak. So when we understand that something important to the patient that we are trying to address is not addressed in a proper way, or the outcomes are suboptimal, then we have to do research. So we do research again when we have weaknesses in listening, in planning, or in the action that we implement. And I think that today we'll see very nice presentations from an international audience. We have Stefania Fatone from the United States, Hirobara from Japan, Andy Hanson, again from the United States. And here we have the honor to have in presence Michael Shaffer from Polig, which is a very nice pleasure to have international guests here today. But before leaving the floor to our international guests, I would like to just very briefly, to save a little bit of the time, to express what we do in terms of applied research in the technical area at Centro Protesi. So as we tried to express this morning, and Gregorio Teti, the director, was explaining, what we want to do is to innovate OMP production to ensure performance and comfort, and also to improve the consistency of outcomes. And the way we want to do it is to introduce new casting methods, to introduce digital processes, to invest resource and intellectual resource, not just in terms of monetary resources, in material integration, material innovation, mechanical testing, and biomechanical analysis. And I would like to very briefly show you some examples of what we do in sport, because sport, as we already mentioned this morning, is a challenge. And as you can see here, the guy that's gone to WIT is one of our patients. Actually got an injury during his work, so an Inail patient, and he now can run the 100 meters in Berlin in 10:84, which is much less than what we might do with 2 able-bodied legs. Okay, so it's very important what we can do with our prosthetic work. So very briefly, starting from the casting methodology, we invested in a new casting system, and we try to understand exactly how to use the system, which is based on hydrostatic suspension that gives basically the feeling to the patient of a glove surrounding the body when using a socket. So we do this casting, we do the rectification in a digital way, where we can monitor the way we make changes, where we add materials in red here, and where we remove material in blue. And we can create sockets that are substantially different from the one that Gregorio showed this morning, where we can improve, we believe, the patient comfort, which is, as I said, the ultimate goal, without compromising the actual effectiveness of the gait. And in a introductory work, preliminary work we did in 2019, we showed that with this new type of socket, we can increment the socket comfort by 3 points over 10, which is excellent results, which pushed us to participate in a project which is actually financed by the Department of Defense of the United States. And we are doing that in collaboration with the Northwestern University of Chicago and the US Department of Veteran Affairs in Minneapolis. The digital process is the topic of Michael Shaffer, and he will show how Polig is really one of the leaders in this field. We are very honored to have you here, because you are very innovators in this aspect and in patient care in general. And we want to change from a 100% manual process to a process where we do bespoke products, so it's fully custom, but we use standardized processes, and we can monitor what we do in a better way through scanning, testing, in bench testing, in silico, so virtual testing, post-market clinical follow-up, and all these technologies together will give us a better view, a custom view of what the patient are able to do with our devices. And most importantly, and I want to point to the right side of my slide here, is to really try to check if we are able to make a good match between the technology and the patient, and understand if the technology that we try to conceive is really appropriate, or if we have to change. It's possible, and if we have to innovate. So if we don't follow a digital process with testing, we don't know enough about materials, we don't know enough about what we do, and we don't know enough about the outcome. So it's very important to monitor evidences, to improve and increase and support innovators in knowing more about their materials and the processes. Of course, the digital world is growing fast. We know it's Industry 4.0. There are many scanners that we can exploit. We also developed our own scanner in collaboration with a company next to Bologna for a full body scanning. We can scan large parts and very detailed parts. We can do rectifications on the computer, and it's pretty standard. But what is coming out from this project with the US Department of Defense is the possibility to create a software which is customized on the prosthetist. that can learn from good fit, can learn from the prosthetist and embed the knowledge of the prosthetist into the software. That will make suggestions that the patient will accept or not, sorry, that the prosthetist will accept or not accept. And this is based on very advanced computational geometry methods based on morphing technologies and machine learning. So we think we can pave the way to a completely new way to do CAD modeling in prosthetics and orthotics. Of course, we have carvers, we show that, we have 3D printing, and we talked a lot about 3D printing with the fantastic project that Inail is also supporting, and Internet of Things, of course, that will give us the on-the-field view of the patient's activity, which is of ultimate importance. Material integration and mechanical testing are fundamental to really give the comfort to the patient and the mechanical strength. I'm very proud of this activity we are doing, thanks to Inail in collaboration with the University of Padova, about socket testing, about special component testing, because there is no standards available, and we think we are very pushing the limit of the knowledge in the field at the moment. We are doing tests on materials with Polytechnic of Milano and the University of Padova. We are moving toward the in silico testing, okay, because we want to do tests that are easy to run on a computer more than on a bench. Bench is the validation, but we want to have easy way, fast ways to do developments. And again, we have fantastic partners to do that. But really, I want to close my presentation with some examples, because I think this will give the sense of what we do. So we had this patient with a young lady with hemiplegia that was running and long jumping. She's a national athlete, and she was using a custom solution till a couple of years ago. And then she had an injury and she was not able to use it anymore. So we had to come up with a solution for Tokyo. She wanted to go to Tokyo, so we had to find a solution for her. It's mandatory with the limit in time. Something had to be done. So we really tried to combine digitalization, pre-preg technology development, and we created an orthosis which is custom made, which fits into an athletic shoe, and that doesn't create any pain, that is modulated in terms of stiffness from the sole to posterior bar, and she gained a possibility to compete in Tokyo. So this gives us great proud for her. And the triathlon is another great application. We have a fantastic athlete, and this is thrilling and emotional to tell you. She had meningitis when she was younger. She's bilateral, upper and lower. She has partial finger loss. She has partial foot amputations with range of motion limitation at the ankles, with a very delicate skid as typical from meningitis. And again, we try to push again the limits. We try to make prosthesis to be very lightweight, but able to sustain all the training that is required and all the competitions. And we use some biomechanical analysis to optimize, but really the great success is to see her competing in Tokyo, to pass in front of us when we were waiting along the streets with the colleagues, and to see her closing with the bronze medal in this great competition. So Veronica is a great athlete, and I really recommend to go and see her film to see her story in more details. It's very emotional to tell the story. And another example regarding sitting volley, a very rare disease, Cleodemia. This patient has a bilateral and grip fingers, very delicate with a fixed posture, and she has to play volleyball. Sitting volley. So she has to receive impacts and move around the field with her hands. So the problem, the challenge here was to create something that she could use as an orthosis on top of her hands. So we did the scanning, we used some advanced modeling techniques, and we used 3D printing in a water-soluble solution to create a mold on top of which we could use carbon fiber to make a shell. of the orthosis, and then we glued silicone on top of this laminated shell to create a very soft interface. And we came up with a device which is soft on the inside and has a shell on the outside, so she can reliably hit the ball and move around the field. And again, here is she competing in Tokyo with the Italian team at the Paralympics with the good success, and it's a good results for them to be in Tokyo and being able to do that result. So then I really want to close my presentation with the very last bit. We talked this already. Professor Petroni already introduced that in the morning. Alignment is essential, and it is essential for sport. And this activity started from the intuition of a colleague of ours working in Rome, Gianluca Migliore, a fantastic technician that we love to work with. And we created a nice team and tried to move away from the standard way we align a transfemoral prosthesis for sprinting. So the idea was just to look at what able-bodied runners, sprinters do, which is to keep their thigh flexed when they run in mid-stance, easy. It's around 12 degrees. So we said, why should we align the socket with a 5 degrees inclination when we know that people run with a thigh which is flexed 12 degrees? So we completely changed the alignment. We changed the way we fabricate the socket. And we did a test in Budrio with University of Padua with sensorized feet to try to see if the outcomes were good or not. We went to Tokyo to the laboratory of Professor Obara that is going to talk in a second to do test on Martina Caironi. And we managed to understand and published in Prosthetics and Orthotic International that with this new Inail physiological sprinting alignment, that's the way we called it, we can improve comfort, we can increase propulsion, we can decrease effort, and we keep safety optimal. So unfortunately there was the COVID, so we could not really go and do more tests on more athletes, but there was a test that was very difficult to replicate in the lab, which is an Olympic competition. So the same alignment was done on all our three top runners, on all the runners of Italy. And I think that this result with a world record with 3 medals really shows that what we are doing is meaningful, which is of course really thanks to the very big commitment of these fantastic ladies, and we hope we gave them a little bit of help with our technology. So just in conclusion, so Inail, I believe, is really everything about personalized healthcare. So we want to do something special, something central to the patient with the best technologies and know-how that we can have at the moment. So with this hopefully brief introduction, I would like to give the floor to Hiro Bara that is connected from Tokyo. So Hiro, if you are there.
Yes, I'm here.
Fantastic. Thank you. Excellent to see you.
Yep. Okay.
Thank you.
Okay.
So you can share the screen and the floor is yours. Thank you.
Yep. Okay, can you hear me? Oh, nobody's there. Okay. Can you hear me okay? Good.
Yes, we can hear
Yes,
you.
Hiro, fine.
Okay. Okay. Thank you very much for your kind introductions. And thank you very much for giving me an opportunity to talk. And thank you very much for inviting me to the great conference. Today, I'd like to talk about the asymmetric running mechanics in the unilateral transfemoral amputees. The transfemoral amputation is a surgical procedure performed to remove the lower limb at or above the knee joint when that limb has been severely damaged via trauma, disease, or a congenital defect. The one point is that the unilateral transfemoral amputees does not have a biological knee and ankle joint. Consequently, they have to use a prosthetic knee and ankle joint to stand up and walk and run. Even if the current functioning prosthetic technologies, the increased demand for the mobility is very severe problem for these populations. This slide shows that how the locomotor function in unilateral transfemoral amputees are deteriorate after the amputations. The left and right panels indicate how much the distribution of the walking aids at home and outside of the home. From left to right, the transtibial amputees, knee disarticulations, and transfemoral amputees. The green bars indicate no aid when they want to walk at home, and the right panel indicate their walking aid in the outdoors. So when we take a look at these figures, the very low function of the locomotion in unilateral transfemoral amputees after the amputations. The running is one of the most typical example of their active exercise in the human being. So a previous study asked the transfemoral amputees, are you able to run or not? So according to the statistics, the transtibial amputees said yes, around 30%. So on the other hand, the less than 5% can run on the outside in the unilateral transfemoral amputees. This means that the running is very demanding task after the unilateral transfemoral amputation compared with the unilateral transtibial amputation. One of the reasons may be that the unilateral transfemoral amputees have to use a lot of the prosthetic components when they want to run. The first is a socket. They have to customize and individualize the socket because according to their stump limb configuration and shape. And also they have to use a prosthetic knee joint. So generally the prosthetic knee joint is not so diverse now. There are only the one or two options with the 1 degree of freedom, like the flexion and extensions. And after the pylon and adapters to connect with the prosthetic knee joint and prosthetic feet. So yes, the running specific prosthesis is one of the biggest remarkable characteristics of the prosthetic component for the running in the unilateral transtibial and transfemoral amputees. The running specific prosthesis is made up mainly by the fabricated by the carbon fiber reinforced plastic. The running specific prosthesis is characterized by the lightweight foot compared with the biological leg. There's still pros and cons, but generally the function of the running specific prosthesis is like a springy leg and spring function, but nobody knows what's the truth. So before this talk, so our team members performed the systematic reviews, how much publication are there about the unilateral transfemoral amputees and its running activities. So we performed that the PubMed search and Scopus and other engines, and then we performed that how much publications is published so far about the unilateral transfemoral amputees and its running activities. What we found is that the less than 30% of the publication deal with the unilateral transfemoral amputees. In other words, the more than 70% is about the transtibial amputees. So we need more accumulated knowledge about the transfemoral amputees and its running activities. So in this talk, we would like to specifically talk about the ground reaction forces. The ground reaction force is one of the most fundamental parameters in the biomechanics. The ground reaction force loading generally associated with the injury risk. If the GRF loading is greater, injury risk also greater. Okay. Further, the ground reaction force is very important parameters to predict their athletic performance, like a running speed or sprinting performance. Okay. So additionally, the very fundamental ground reaction forces are very useful for the prosthesis research and development, as well as the gait rehabilitation to reduce the injury risk or more effective gait training. So in this talk, we would like to deliver about how the ground reaction force modulated after the unilateral transfemoral amputations. So here's my research question. So are GRF the asymmetric or symmetric during running in unilateral transfemoral amputees? Everyone knows that the unilateral transfemoral amputees are morphologically asymmetric because they lost biological tissues in one side, so morphologically asymmetric between the legs. But how was GRF and functionally asymmetric or symmetric? This is my research questions. First, we perform the biomechanical testing in our research institute. We have invited a couple of the world athletes to the Tokyo, and we performed the biomechanical testing to investigate their ground reaction force. So in this talk, we will not talk about the joint moment or joint kinematics and other biomechanical parameters, but we also measured such parameters after our experiments. So this is a movie for the world champion, the unilateral transfemoral amputees. We asked him to perform the straight running over the 50 meters long in the laboratories. And next is the side view. And we set the 7 force platforms on the runway, and then they pass, and sometimes they hit the ground and correctly. The point is that his stump legs is much smaller volume compared with his intact leg. It's completely different size. It's back views. Surprisingly, his torso and his the backside is very squeezed and it's all waved. It's not completely different from those of the able-bodied athletics running. And also his right leg is a 4-foot strike. His heel never contact with the ground like that. This is his characters. And we cross-sectionally compared these characters, like ground reaction forces, to the other able-bodied counterpart, and as well as other unilateral transfemoral amputees. And here's the main results. From left to right, the vertical, anterior posteriors, and medial lateral ground reaction forces. And red and blue lines indicate prosthetic leg and intact leg, respectively. X and Y axis indicate the percent stance phase and ground reaction forces divided by the body weight. The first, we found that the prosthetic leg has less vertical force compared with the intact leg, very small peak of the vertical GRF. This may be due to their atrophy and passive running specific prosthesis. And next, when we take a look at the anterior posterior GRF, the prosthetic leg has very small braking forces compared with the intact leg. Okay, so smaller braking forces is one of the character of the prosthetic leg, and also the prosthetic leg switched from the negative to the positive in the more earlier time compared with the intact leg. This means that the most of the transfemoral amputees can use the less small braking forces. Rather, they can use more long time for the propulsion of the bodies. It's completely different running mechanics. The very surprisingly, the medial lateral force in the prosthetic leg is pretty close to the zero compared with the intact leg. This means that the negligible small medial lateral force is like a tightrope running because there are no flexibilities in the medial lateral direction in their running specific prosthesis. They have to put their feet on the ground in the correctly. So that's the reason for the very small medial lateral forces. These data are derived from the overground maximal sprinting. And next, we further confirm this phenomena in the instrumental treadmill by changing the running speed gradually. So we perform this running technique in the instrumental treadmill. This is made in Japan instrumental treadmills, and we use these devices to investigate ground reaction forces and spatial temporal parameters. And here's a movie for the unilateral transfemoral amputees who run 21 km/h, and his left leg is intact and right leg is a prosthetic leg. And in the right panel indicate the vertical ground reaction forces according to the time course. I will just simultaneously show the both data with the synchronized data. And first is intact leg ground hit and very peaky and greater forces, and a prosthetic leg hits the ground, but very small peak. Okay, it's almost half values. And next, an intact limb again, and greater forces, and smaller forces in the prosthetic leg. And as you can see, the prosthetic leg cannot produce a greater force like an intact leg. It's very easy to understand how the prosthetic leg has a negative effect for the force production capabilities compared with the intact leg. And we also systematically changed their running speed from the 30% to the 70% of their running maximum speed. And then what we found is that the prosthetic leg cannot produce a greater force compared with the intact limb. So the less vertical GRF production capability is one of the characteristics of the prosthetic limb in unilateral transfemoral amputees. We are not sure why they cannot produce greater force in the prosthetic limb, but one potential explanation may be due to the atrophy and passive RSP devices compared with the biological tissues in the intact limb. Next, we check the anterior posterior GRF, and the left and right indicate the intact limb and prosthetic limb respectively. In both figures, negative and positive data indicate the braking forces and propulsive forces, respectively. What we found is that the intact limb has greater braking forces, and on the other hand, the prosthetic limb has less small braking force. Instead, they can produce more greater propulsive forces in the later part of the stance phase. So the smaller braking forces and the faster anterior-posterior transition is a very unique character of the prosthetic limb. As a consequence of these GRF profiles, the unilateral transfemoral amputees accelerate their center of mass in their prosthetic limb step, but decelerate in the intact limb step. So this may be due to the rollover RSP shape, because they cannot breaking the force a lot. Finally, they are running a specific prosthesis roll over in the earlier part of the stance phase. So just in case, the greater braking force is very indicative of the Achilles tendon injuries in the runner. So they have to take care about their inductive care to prevent the further injuries. So as I mentioned in the earlier part of this talk, the ground reaction force can be a predictor for the potential injury risk. For example, in the vertical GRF shown in the right panel here, so the vertical GRF show the two types of the slope. The first is the initial slope and the later part of the second slope. For the first slope, from the beginning to the first peak, we can calculate the vertical instantaneous loading rate. Okay, so the vertical instantaneous loading rate indicate of the tibial stress fracture risk and plantar fasciitis risk. So if the vertical instantaneous loading rate is increased, this musculoskeletal system may be exposed to a higher risk of the injuries. So what happened in the unilateral transfemoral amputees when they perform the running? So we calculate their vertical instantaneous loading rate in unilateral transfemoral amputees when they change their running speed from the 30% to the 60%. From left to right, this result indicate the prosthetic limb, intact limb, and control limb without amputations. So X and Y axis indicate the running speed and the vertical instantaneous loading rate. So if the vertical instantaneous loading rate is greater, the injury risk may be greater. So what we found is that intact limb is significantly greater compared with the prosthetic limb and control limb in all running speeds. And these results indicate that the intact limb of the unilateral transfemoral amputees may be exposed to a higher injury risk compared with their prosthetic limb and control limb in the non-amputees. So especially the vertical instantaneous loading rate are known to be associated with the tibial stress fractures and plantar fasciitis. So they have to take care about that before and after the running activities. And finally, I'd like to show our new system to investigate and evaluate their athlete performance on the treadmill. So we especially customized the treadmill to calculate the instantaneous belt speed according to their anterior-posterior force productions. So if the subject perform their posterior forces, and finally the system calculates the instantaneous velocities and to the next step. And then finally they can naturally accelerate their body during the treadmill running. I will just show the movie here. 1, 2, 3, 4, 5, 6, they gradually accelerate in their natural way, and finally they reach the maximal running speed on the treadmill. I will just show the more half speed, and then he gradually accelerated, and then after the acceleration, he reached the top running speed. The point is that during the acceleration, we can continuously measure the ground reaction force in the vertical, anterior, posterior, and medial lateral component. Briefly, I'd like to show the result. Okay, X and Y axis indicate the time course and ground reaction forces. And the black lines indicate the instantaneous velocities on the belt. For every step, he can accelerate his center of mass on every step like that. Okay, and then finally, his instantaneous velocity reached his maximal speed, like 23 km/h. Okay, and red and blue lines indicate the prosthetic and intact limb respectively. The lines indicate their vertical forces, and painted area indicate their anterior-posterior impulse. So please take a look at the anterior-posterior impulse. From the first step to the eighth step, they are greater positive impulse in their propulsive or components. So this means that this subject accelerates their center of mass by using the 8th step. And after the 9th step, their negative and positive impulse almost equal between the legs. The point is that there's the blue lines, the intact limb has much greater propulsive impulse compared with the prosthetic limb, especially for the 4th step, and 6th and 8th step produce much greater propulsive impulse compared with the red prosthetic limb. This means that the intact limb may play a major role for the acceleration in the sprinting. By using these systems, now we are measuring a lot of the athletes. How can they accelerate their center of mass during the sprinting? Okay. Let me wrap up the talk. Here's the take-home message. So my research question is that unilateral transfemoral amputees are morphologically asymmetric, but how was it functionally? So my answer is that their running mechanics is functionally asymmetric during running. So we measured lots of their biomechanical parameters after the experiment, but almost the 99% of the parameters are asymmetric between the legs, except for their subjective feeling. Uniquely, somehow, the most of the subject told me that their running style felt like more symmetric in their psychological way somehow. Okay. So we found that the greater loading on the intact limb during the stance phase. This means that the intact limb may be exposed to a greater injury risk compared with the other leg. However, the intact limb will play the major role for the performance. This means that intact limb reliant performance is also the important point to understand the unilateral transfemoral amputees. As a consequence, the double-edged sword may be the important point for understanding the intact limb. So I'd like to thank for inviting this great conference, and then I'd like to say thank you very much for my special thanks to all the members and my colleagues. So I'm happy to take any question. Thank you very much.
Thank you very much, Hiro, for your very interesting presentation, very detailed presentation. I think you're really at the front head of biomechanics for sports biomechanics and Thanks. In amputees. I don't know if there are questions from online. It's an unusual situation where you do these events online. So Hiro, just very briefly, one question for you. It's about the role for me. It's about the role of propulsive impulse. So how we can prevent injury in the intact limb of amputees? Special shoes, special training. What do you have in mind?
Yeah, well, it's a really good question. Actually, there are several strategies to prevent such an overloading in the intact limb. But in my experience, the best way to prevent such a potential risk of the intact limb may be to reduce the exercise volume. That's very important. They have to control the exercise volume in the weekdays or the weekends. Sometimes they perform a lot of training with their able-bodied counterpart to compete each other, but it may be the bad way. So probably they need to reduce the exercise volume every day.
Control it very well. Okay, I understand. Yes, it's cumulative traumatic injuries that we have. Okay, thank you very much, Hiro, for your presentation. It was an honor to have you with us today. And without further time, I'd like to pass on the floor to Michael Shaffer. Thank you.
Okay, thank you very much.
Thank you. Yeah, ladies and gentlemen, Andrea, thank you very much for this invitation. It's a big pleasure to be here for such an outstanding jubilee, 60 years of Centro Protesi. And coming from a patient care facility in the very south of Germany, we have in between the past 30, 35 years developed into a company with different destinations all over Germany and with a deeply specialization in individual patient care. So 90% of our daily work is really individual work for patients, prosthesis, orthosis. And this was mainly developed by a person called Kurt Polik. He is the third generation of the Polik family. And he took over together with his wife, Sieglinde Polik, the company in 1981. I should tell to the audience the very best and warmest greetings from both of them. They give me the address to you. And in 1983, he heard a presentation from a former professor from Heidelberg, Ernst Marquardt. He was a deeply specialized in the treatment of congenital malformation in patients. And he said, without specialization, we would not achieve any progress. So this is a philosophy that Kurt Polik brings into the company, and he deeply specialized all the different fields. And when I wrote here 1981, 27 people, it's a result out of this work that in 2021, we have 627 people with different areas, different specialities. We build up from year to year new teams, new specialized teams. And in between, the prosthetics, which were nearly 100% in the beginning, now are probably 30%. And we have a big field of children orthopedics and a big field of orthotics as well inside the company. And a lot of things happened since then. So when I see the invitation from Andrea, and it was, of course, it was, we did a 100 years anniversary, exactly nearly 2 years ago. It was the last conference before Corona. And we've had very well-known speakers, international speakers inside this conference, as you can see here. And one of them in the program was Andrea Cuti, coming from Inail. And we was very proud, Andrea, that you was with us. And he is such a great expert in showing the Inail way to all of the world. It's very impressive, and we are very thankful that we could keep the contact to Inail over all these years together. And he represents successfully concepts in lower extremity prosthetics. And there were two points in the core concept called quality and satisfaction. And I think in everything that we are doing and what we are speaking about, the main important thing is that we focus the patients and the patient needs at least. And this is coming out very well in your lecture. And this is as well something that we address too. So when I read I primi sessant'anni, I understand for my first time why there is a wine in my cellar called Sessant'anni. I always thought this is a family name, a family name of the family Sessant'anni, and it's a primitivo from Mandurio. And when I see the invitation, I say, oh, Sessant'anni, because the grapes are Sessant'anni old. And so it was a déjà vu, let's say. 60 years of prosthetics in Centro Protesi, and it was driven, we heard the name very often today, by Hannes Schmiedl in the beginning. And Hannes Schmiedl was as well the contact for Kurt Polik in 1988, when he has visited first Budrio and have a look, because Budrio was always deeply specialized in prosthetics, and that was a topic of Polik as well in the late 80s. And I remember that Kurt Polik came back and said, oh, we have to specialize our production. They have people who are running the lamination team. They have people who are running the cosmetic team and so on. And this was the beginning when we did specializations as well at Polik, and where we get the inspiration out of Hannes Schmiedl and his team. Rinaldo Sacchetti was as well in, and so this was the inspiration that we took from Inail originally. And Kurt Polik always was very, very engaged in new socket technologies, in new prosthetic systems, and defining a way for CAD/CAM socket in Germany and a special procedure how to create it at its best. He revisited Budrio in 1991 with a course of CAD/CAM socket technology, and you may see some people that you know. There is Hannes Schmiedl in two pictures in the middle, and Kurt Polik, you can see him in the second picture and in the first picture. And on the right side, I think it's Mr. Verney, isn't he? Or probably another one from your team. I'm not pretty sure, to be honest. But so we have always a good contact to Budrio and his team. So coming to my topic, sense and nonsense of digital concepts and workflows in O&P. So I'm sure digitalization is everywhere around the world and everyone is speaking about. And I want to make sure that we are speaking on the same thing when we are speaking about that. And there are different factors why we are speaking about digitalization. In Germany, for example, we have the situation that there are some big changes in community, in society. The people are getting older, and if you contribute to 1910, we don't have so much young people coming up in our profession, coming up in our society, and therefore the market is growing much, but we don't have the experts for the work. That's a big problem in Germany, that we could not address our work to the quantity of people, and therefore we do a lot of efforts in educating people, but still these are not enough. And if you see the different numbers and the different graphics, you can see that there are less people coming into our field, coming into our market, and our profession especially is one of the 10 most shortages occupations. So we don't have enough for them, and therefore digitalization for us is a need that we could handle the market in the future and to develop the market in the future. Even if we know that it's very disruptive as well in our origin profession, it's a handcraft profession, and we're speaking about digitalization, digitalize processes and so on. We have to make sure that it makes only sense if this topic can offer added value to us, even if it's in the performance or if it's in the way how we're going to perform it. And we have to make sure as well, if it won't be able to offer an added value, it's nonsense. So it makes no sense, at least, to step into these topics. So we have three big parts where we're looking on digitalization. The first one is digitalization of the administrational processes. We're thinking about a digital patient layout, a paperless office, at least, with digital patient files, and with an implemented digital guidance in our workshops, where we can lead the patient through the whole process of treatment. But today I will focus on digital workflows in our workshops, and as well on digital processes in production side. So the old process, let's say, starting with consultation, you give different topics to the patient and look on his clinical situation, do the castings, model it, and thinking about constructional sites, produce, finish it, and in between you fit it and you try it out together with the patient. The process didn't change that much, but we have other methods to maybe focus on and to make this process more efficient. And so today, if we speak about a digital process, we're speaking about probably scanning, probably digital modeling, probably digital construction, digital production, finishing, and at least we still have to do the work with the patient and have to pick up the patient needs. And we have to make sure that we won't lose any quality in our work by implementing such methods. And we have to rethink our work, how to use it at its best. I have here a sample from a company. It's taken out of the internet, to be honest. And this, in my opinion, is not a way how it works. It shows you that this is where you meet up with your patients to assess their conditions and recommend the right brace for the right job. Then scan the patient body, and last step is to follow with your patient to ensure that they are happy with our services. So just produce, we send it to you, you send us a scan, we send to you the product, and everything is working well. That could not work, to be honest. I'm very sure that could not work, and that will not offer the quality that we need for our patients. So individuality in the treatment is still a recommended need that's in the primary focus. So looking into prosthetics, of course, we are thinking about scanning patients, scanning stumps, because if I give a patient to 10 different certified prosthetists, you get out 10 different prostheses. And it's difficult for us to focus on quality. What is quality? And we want to serve our prosthetists, that our prosthetists can serve to the patients a pretty same quality and a pretty same way how to reach this quality. So therefore, we invest a lot of time in gaining data, in gaining measurements on a defined way, not on a feeling of a prosthetist, but we have special measuring tools, and we collected all the data over years and treat the patient, get a good final socket and measure the final socket, and creating an algorithm how to come from a stump to a good fitting socket at least. So therefore, a lot of work is spent into this work. And of course, we implemented simulations as well for probably doing simulations of volume of a stump. We have to come in the view out of the circumference measurement into a volume measurement to look on the patient stump as a volume, not only as a circumference measurement. And therefore, we have done a lot in let's say, in analyzing how to reach the best performance in a stump modulation and in a stump tissue implementation inside our new socket types. In the field of orthotics, to be honest, we completely changed the point of view. If you know, when we take a plaster cast out of a patient's hands or of a trunk for a scoliotic brace, let's say, we always make a plaster cast around and we focus one position. And this one position is focused in the cast, but we didn't know if this is the right position or if this is the final good working position for the patient. So we thought, what can we change in this process coming out of the traditional plaster casting technology? And we thought, if we can reach, before we take the body scan or before we take the body measurements, if we can reach a situation where the patient can feel the correction of his deformity, can feel how it feels when my hand is in a good position or when my trunk is in a good position, and we scan, then we have the final result in the beginning and not at the end of the process. So therefore, we developed a system called SimBrace, which is here for spinal orthosis, for a scoliotic brace. And you can see the theory. We implement a system where we can adjust the human body in a well-corrected way, and we can leave the patient's inside the system for, let's say, 15 minutes for test it out, how it feels when the body is corrected. We have some young girls who are nearly collapsing inside because the correction was too much and they could not realize it with their bodies. But you get an information which is very important in the beginning and not at the end of or in the middle of the treatment. So therefore we are working with the system and we adjusting the body onto the traditional methods, how we handle a scoliotic topic. Then we do the scan of the body, which is much nicer for the patients, to be honest, not to get wet casting, plaster cast around the body, only getting these scanning, a touchless scan around the body. And then we're going to the modulation. This is another topic. This is the sim brace for the upper extremity, where we can adjust the hand in a three-dimensional way, the complete extremity, and then we can try out with our therapists how probably for a daily orthosis the function of the hand can be realized within these correction, and we sometimes go back little bit of correction because we see that with too much correction the patient cannot grip anymore or cannot run his hand in a good way. So therefore, as well here, we got a very good result in the early beginning before we take the cast or the scan of the patient. And then if everything went well, if the function of the hand is in a good way, we make a scan and have these position already inside our digital model. So this is a change of paradigm in the way how to handle these topics. In between, in the field of orthotics, we changed between plaster cast and scan up to 94% actually. In 2021, 94% of our patients were scanned for orthotics. In prosthesis, it's a bit less because in prosthesis we have to realize several correction situations. So we probably have about 50% in prosthetics, but in orthotics we have nearly 100%, 94%, and there are still some cases where we don't get a good result and where we have to handle that topic as well in a traditional way. Anyway, our technicians, they have to move out of the plaster casting room into a computer room, but they all realized it in their work. So they have the biggest know-how of how to treat a body shape, a plaster cast. And out of this experiences, they go back in the modulation room, do the modulation of the extremities or of the human body of the digital model, and afterwards it goes into our constructional team who is creating the orthosis out of the different measurements that we took in before. We are working in some cases with bots, mean automized situation, workflows where we defined which step is coming afterwards, and with templates inside, and it runs in a very nice way. So according to digital production, there are different steps necessary. You have to implement it first into your team. You need to have several additional job profiles, let's say like a CAD technician who can run a machine, who can adjust the machine, and as well to implement different machines and different technologies and different scientific backgrounds to materials at least. So what is the advantage in 3D production? Of course, we can create much more interesting constructions, three-dimensional construction with different adjectives, let's say like a soft touch implementation. We can create joints, we can create closures, and a lot of things that we could not handle in a custom way by handcrafting, but which is very important. And if someone asks us, do you print everything? We say, no, definitely not. We only do a printed job if we can gain any advantage inside the constructional side, inside the performance of the final product. So if you look on the web, and I did a Google search, 3D printed orthosis, you will get a lot of orthosis looking like traditional stuff. This is not the way, in my opinion, how to handle a topic like 3D printing, because if we make the same product out of new material, to be honest, a printing powder is very expensive. It's not a cheap way to produce such products, such individual products. This is not the way. So we have to gain any added value inside when we are using this technology. We have to make sure that there is an added value and not only copy old stuff into a new production method. That is not a way. And especially if you ask me about prosthesis, up to today, I didn't see any socket that really shows me that it's worth for thinking about printing sockets in a three-dimensional way, because we have very lightweight sockets, we have very dynamic socket, we have extremely good materials in that performances, and until we could not develop better materials in this area of 3D printing according to mechanical properties and so on, I think we could not reach the way of really digitize sockets in production, actually. But these are examples who are running very well. Upper extremity orthosis, where you don't have the full body weight onto the product, where you have to correct different deformations, and where you probably can construct breathable situation, which makes a much better comfort. You can use the design options to design the orthosis in a nice way. We have, for example, children coming from the kindergarten and telling, oh, I have friends over there, they want to have the same brace like I do because it looks so great. And this is something that helps us a lot if we see that a child, for example, is willing to wear a brace for getting the correction because of its design or its outcome, then it's a big step forward for us, to be honest. And here, for example, you see a highly developed 3D printed product that's for children with obstetric brachial plexus palsy. So palsy coming up from the birth, and we've integrated, therefore, different constructional parts like dynamic rotation modules for supination and pronation that can be adjusted in a dynamic way. We have integrated different construction topics like a trunk module, a double ball unit where you can three-dimensionally adjust the extremity into that position that is needed from the doctor side. And we have a high success in treating these children because the device is accepted in a very well way. Here you can see a 3D printed partial hand prosthesis for a child. She only has two pinky fingers, the small ones, and therefore she cannot grip a lot of things. And with the hands, she can drive the bicycle. She's doing a lot of things in daily living that she cannot do without. So therefore, it's like a tool for her. It's not a prosthesis like wear it the complete day from the early morning to the late evening, but it's a tool. It's a tool that she can use in a lot of different activities in daily living where her hands only are not able to perform. Here is a body-powered orthosis from a patient. He's a lawyer, a very successful lawyer, and he has an accident in a lake, therefore a tetraplegic one, and he has no finger function, but he still have his wrist function, and he's a really engaged fly fisher, and he was so depressed because he could not go out and do the fly fishing procedure. And he came to us from far away, from Berlin to Traunstein, because he heard that there is something special and probably we can help him. He was in a lot of places before that could not help him. So we developed a silicone orthosis on the right side. You can see it here. the root hand, where he can grip the root in a very well way, and he can perform the line out, throwing the line out in a very well way. And for the left side, it's the line hand. He has to grip the thin line of the root for performing the fishing, and you can see it in the next slide. I hope that the volume in the movie is running well. Can you turn out? Oh no, it would not work, unfortunately. So you have to probably look on the pictures. Can we run the? Sorry. It was. Ah, okay. Ah, yeah. Normally there's a voice in the background, but it doesn't matter. You can see the function here on the left side, how he performed the gripping of his non-functional hand, and you can see how he can strip the line a little bit later in the video, and we make something special for his wheelchair where he can adjust the line when he took it in out of fishing. He explained us everything what is necessary around the topic, you can see, and our people really put in a lot of efforts and a lot of thoughts how to realize it at its best. But at the end, we have had this discussion in Germany too with doctors. They told me, oh, this is not a typical patient that is in my practice in daily living. But when I tell you what happens to him afterwards, he got so much motivation doing other things, so much motivation in his daily living. So it was absolutely like a key to really activate his life in a better way, because he can handle his main topic at least. So to come to the conclusion, respecting all digital developments, digitization can only be one of several tools. At least the outcome of our patients has to be the primary focus of our work. That's the most important thing. Thank you very much.
Thank you, Michael. It was very impressing how you intended to implement digitalization and it's I believe it's very important to, and the topic of today was really on that same page. It is really important to keep in mind that we need to take value out of something, otherwise it doesn't make sense. So it should not be just an engineering tool or game or playground. It should be something that we can return value to the patients.
To be honest, it's the patient's eminence that is in the background, not only evidence. Evidence is important as well, of course, but bringing more into the treatment for our patients and more value, that they use it, that they create it, and the children really react great on such stuff. To be honest, and for us, the most important is that the children wearing their orthosis, that they can help, that they can improve their daily living.
It's really impressive, really impressive. Thank you. Okay, so I believe we can move on to the next speaker. Stefania Fatone should be online, I believe.
Yes.
Stefania, hello. Good to see you.
I'm here.
We have to double check that the translators can hear you well. Is it okay? Yes, it's working. Yeah, you can share your screen.
It is my great pleasure to participate in Inail's 60th anniversary conference. Felice Anniversario. I want to thank my colleague and collaborator, Dr. Andrea Cuti, for the invitation to present to you today on work we have conducted at LUPOC over the last decade, developing a subischial socket technique for persons with transfemoral amputation. I'd like to acknowledge that most of the work that I will present today was funded by the US Department of Defense, and that it would not have been possible without the help of my colleague and co-developer of the subischial socket technique, Mr. Ryan Caldwell. I'd also like to acknowledge our collaborators at Sheck and Cyrus and the Jesse Brown VA Medical Center, who have assisted in many different aspects of the project over the years. I wanted to begin by providing a brief overview of our decade of work trying to develop a more comfortable socket for people with transfemoral amputation. The idea for a subischial socket began in Ryan's clinical practice when he experimented with using active vacuum suspension for people with transfemoral amputation. Ryan had had success using active vacuum with transtibial amputees and wanted to see if the same improvements in suspension and wound healing would be of benefit to transfemoral amputees. However, sealing the liner at the proximal edge of the socket proved difficult and led him to reducing the proximal flares and then the height. After receiving very positive responses from his patients during clinical trial fittings of sockets with lower trim lines, Ryan came to LUPOC with his ideas for a subischial socket in 2007, and we initiated a conversation about how we could work together to further develop the concept of a subischial socket. This started a long process of writing and applying for funding to work together on this idea. In 2010, we were successful in receiving a Technology Development Award from the US Department of Defense. This award funded us to explore the subischial socket idea and led us to developing our technique for fabricating and fitting a subischial socket. We first piloted teaching of the technique to prosthetists in 2015, and since then, we've taught the technique to 263 prosthetists as part of 30 hands-on workshops held in 9 countries. At this time, we also received funding from the US Department of Defense to conduct a clinical trial to evaluate comparative effectiveness of the subischial socket. We published the results of work from our initial grant describing the new flexive socket technique, the rectification process, and some initial case study evaluations. While we initially developed the technique for use with active vacuum suspension, with some minor modifications to the technique, we were later able to describe an approach for passive suction suspension, the new flexive, which we published in 2019. At the same time, we received additional funding from the US Department of Defense, this time collaborating with Dr. Andrew Sawyers at the University of Illinois at Chicago, for a pilot clinical trial evaluating the effects of transitioning to a subischial socket on muscle strength. That work is currently underway. We completed the comparative effectiveness clinical trial in 2020, and the results of our primary outcomes were recently published. A second paper describing the results of secondary outcomes is currently in review. I will present the results of the clinical trial towards the end of my presentation. First, let me highlight for you some of the features of our subischial socket technique. The socket attempts to address a problem experienced by many users of ischial containment sockets, which is currently the standard of care in the US. Clinically, users complain of proximal socket discomfort, and this is also supported by research that shows that ischial containment sockets limit comfort and reduce hip range of motion compared to other sockets, such as the master quad, and as compared to post-osseointegration. The intent of our subischial socket is to have trim lines that don't interact with the pelvis. While the primary goal of our subischial socket was to improve comfort, we thought that if hip motion was also increased and suspension improved, it may be possible to also see improvements in function. Key concepts of our subischial socket technique include that it is a liner-based system. Liners are selected that help shape and compress the limb. As you can see in this image, where the same limb has been cast over 2 different liners, the shape of the limb is different based on how firm the liner is. Secondly, the liner helps provide global compression of the soft tissue, which we believe helps to create a quasi-hydrostatic condition for transfer of weight-bearing forces. Thirdly, it is important that all soft tissue of the thigh be contained in the socket and liner. Hence, the medial trim lines are kept as high as possible without contacting the ramus. The liner and a high socket trim line will help to contain soft tissue and avoid adductor rolls. In terms of compressing the tissue, for our subischal socket technique, this is done first by liner selection. Very preliminary work by Fougeron using an instrumented indenter on a transfemoral residual limb with and without a liner illustrates that wearing a liner helps make tissue less compressible. As we can see in the graph, for the same amount of total force applied to the same location on the limb, the tissue displaced less with the liner than without the liner. Since tissue varies in density and is softest proximally, we recommend using liners with a straight cylindrical profile as they apply greater compression proximally. The effect of the liner on the proximal medial lateral dimension can be seen here in these images. In this particular patient, the proximal medial lateral dimension is reduced by nearly 2.5 centimeters by the folded liner. We use the folded liner when casting to begin the process of reducing this measurement, and then we reduce it even further when modifying the mold. In terms of selecting liners, we prefer silicone liners with fabric for their durability. This is especially important when reflecting the liner over the proximal brim, as we do when using active vacuum suspension. The fabric also facilitates donning as it decreases the friction between the socket and liner when pushing into the socket. Sizing of the liner varies based on suspension method. We prefer to undersize the liner a little for vacuum to reduce the chances of proximal gapping when the liner is reflected over the brim and sealed on the outside with a sealing sleeve. However, firmer liners are harder to undersize than less firm liners. Our preferred liners listed in the table align with those that have high compressive resistance as reported by Kegel in this publication and accompanying liner assist website. Kegel found that silicone liners tend to have a higher compressive resistance than TPE liners, and that the relaxed 3C liner from Ursa has a relatively high compressive resistance compared to other liners. As such, it is a liner that we recommend when starting to use the subischial socket. Unfortunately, very firm liners won't work well with all limbs. Other liners, such as the Ursa sealing, can work well with our technique despite being a little less firm. However, as the liner becomes less firm, the socket has to do more work to be stable on the residual limb. In addition to the compression of soft tissue provided by the liner, additional compression is applied to the limb when we rectify the positive model. During rectification, we recommend circumferential reductions that are gradated along the length of the limb, such that more plaster is removed proximally than distally. When modifying, we take circumference measurements along the length of the cast, staying above the seal when using a liner with an internal seal. The magnitude of reductions is based on initial soft tissue evaluation. In general, softer limbs need more compression and therefore more plaster is removed to achieve greater reductions in circumference and volume. To facilitate teaching our technique, we developed documentation in the form of a socket work form that incorporates a mold reduction algorithm. While volume is reduced during modification, the location and amount of reductions are determined based on whether the subject's residual limb is soft or firm and the residual limb shape. In order to understand whether our socket provides a support over the entire thigh, rather than just being concentrated on the distal end, we conducted a simple clinical study in 13 individuals with transfemoral amputation who were routine subischial socket users. We disconnected their distal components and asked the subjects to transfer as much weight onto the residual limb as they could tolerate in 3 randomly ordered conditions: a bare limb, liner only, and liner with socket. Beneath them was placed a digital scale to measure body weight. If we look at body weight data, we can see that while there was a significant difference in percent body weight between all conditions, the most dramatic change occurred once the socket was donned over the liner. And when we asked the subjects to rate the pain experienced in each condition, while they kept as much body weight on the limb as they could, we saw a significant decrease in pain only when the socket was worn over the liner. This provides indirect support for the idea that the combination of socket and liner redistributes forces away from the distal end and onto the thigh, meaning that this is not an end-bearing socket. Unique features of the technique include that the cast is taken in a seated position and involves only a circumferential wrap over the liner, being sure to capture the proximal edge, especially the medial flare created by the liner, which should be as high in the perineum as possible. This position pre-modifies the limb shape. Modifications of the plaster cast are standardized and involve the same 3 steps for all patients. However, we only remove plaster. We don't do any build-ups. Finally, our socket doesn't require any specific alignment. No pre-flexion is necessary. A flexion contracture can be accommodated if needed, and adduction can be added as needed based on knee length. Socket orientation with respect to the knee should follow the recommendation of the manufacturer of the particular knee being used. In terms of our 3-step mold rectification process, we quantified the changes in shape of 30 molds pre and post rectification to arrive at this rectification map that shows the modifications required for our sub-ischial socket technique. Red indicates approximately 6 millimeters of plaster removed, yellow is about 4 millimeters, and green is 2. The 3 steps of the rectification are to remove plaster proximal lateral to reduce the medial-lateral dimension of the socket based on the measurement taken on the patient. Step 2 involves flattening the posterior aspect, and step 3 is to ensure that these 2 modifications are well blended together. In terms of indications and contraindications, patients in whom you would expect to see some volume change, for example, new patients, should be fit with the passive suction version of the socket with a sealing liner. Vacuum can be beneficial for more active patients where moisture evacuation is needed. At present, the sub-ischial socket requires a liner, so if a patient does not want to wear a liner or has an allergy to silicone, our technique would be contraindicated. While Ryan has used the sub-ischial socket successfully in his clinical practice, we have also evaluated the sub-ischial socket performance through a DoD-funded clinical trial. The purpose of the clinical trial was to compare comfort and functional performance of the new flexive socket to the ischial containment socket in persons with unilateral transfemoral amputation. With ethical committee approval, we aim to recruit 30 participants with unilateral transfemoral amputation to participate in this randomized crossover trial. 2 custom fabricated sockets were worn in random order full-time for 7 weeks with identical testing at 1, 4, and 7 weeks post-socket delivery. The primary outcome was a difference in socket comfort score at 7 weeks. Secondary outcomes included the orthotic and prosthetic users survey to assess lower extremity functional status, health-related quality of life, and satisfaction with device, as well as 3D gait analysis, the 5 times rapid stand test, the 4-square step test, and the T-test of agility to assess functional performance. In terms of gait data, variables related to hip motion and coronal plane socket stability were assessed. We hypothesized that at 7 weeks, the new flexive socket, compared to the ischial containment socket, would provide increased comfort, result in faster times on the performance-based measures, have better lower extremity functional status, satisfaction with device, and health-related quality of life, allow greater hip range of motion, leading to increased step length and walking speed, but not change lateral trunk flexion over the prosthetic limb and step width. 2 statistical approaches were used for comparison of the primary and secondary outcomes. First, differences in outcomes at week 7 were assessed using paired T-tests to compare cross-sectional mean values for each hypothesis for participants who completed data collection at 7 weeks with both sockets. Second, linear mixed effects models were used fit to each outcome. These models use more data points than paired T-tests under the missing at random assumption, allowing us to include subjects with partial data in the analysis. 30 participants were enrolled, with 25 completing the study with full or partial data. Of the 25 participants, 19 were male. Mean age was 46. Mean time since amputation was 23 years. Amputation was due to non-vascular issues in most subjects, and all participants had K3 or K4 mobility levels. All participants received 2 new prosthetic sockets. Ischial containment sockets were consistent with the standard of care reported in the ABC practice analysis and were skin fit with passive suction suspension. New flexive sockets were consistent with description in our original publication, with a silicone liner and active vacuum suspension. Each socket was custom fabricated by a single but different certified prosthetist with experience in each socket, and prosthetic components distal to the socket were standardized within participants. For our primary hypothesis, the mean differences in comfort at each time point were 1.1, 1.8, and 1.5 higher with the subischal socket. Both statistical approaches indicated that the subischal socket was significantly more comfortable than the ischial containment socket at 7 weeks. For our second hypothesis, there was no significant difference between sockets for either statistical approach for performance-based outcomes. For our third hypothesis, cross-sectional analysis at 7 weeks showed no significant difference between sockets. However, when we used all the data across all time points, OPA's satisfaction with the device was significantly higher for the new flexive socket, although the difference of 2.7 at week 7 was small. Gait data were acquired while participants walked at 3 self-selected speeds. When using paired t-tests at 7 weeks, we only saw a significant difference in prosthetic side hip range of motion at self-selected speed, fast speed. At fast speed, prosthetic side sagittal plane hip range of motion was significantly greater than new flexive socket. When all data were assessed using linear mixed effects models, prosthetic side sagittal plane hip range of motion was significantly greater for the new flexive socket at all self-selected speeds. However, only at fast self-selected walking speed was prosthetic side sagittal plane hip flexion found to be significantly greater than the flexive socket. For our fourth hypothesis, there was no significant difference between sockets for step length or walking speed at any speed, regardless of statistical approach. For our fifth hypothesis, there was no significant difference between sockets for lateral trunk flexion or step width at any speed, regardless of statistical approach. As with all studies, there are limitations to this trial. One limitation is that socket systems were compared rather than socket design alone. Anecdotal comments from participants suggested that the new flexive socket was more comfortable due to removal of the proximal brim. This interpretation is supported by a study by Cayley et al., who compared subischial and ischial containment sockets both using vacuum-assisted suspension and reported that subischial sockets were more comfortable. As a further limitation, it is currently unknown how long it takes for individuals with lower limb amputation to accommodate for a new socket. 7 weeks was chosen pragmatically, given concerns that participants would be unwilling to wear a less comfortable socket for any greater length of time. Overall, our results suggest that after 7 weeks accommodation, the new flexive socket was more comfortable, led to greater satisfaction with the device, and allowed greater hip motion than the ischial containment socket in persons with non-vascular, unilateral, transfemoral amputation, and K3, K4 mobility. Furthermore, the new flexive socket did not alter gait biomechanics or coronal plane stability of the socket. If you would like to read more about this work, please see our article in Archives of Physical Medicine and Rehab. While we are confident, based on our experiences using this socket technique with patients and research subjects over 10 years, concerns about the subischial design have been raised, especially early on. For example, in a 2012 article, Harvey et al. Queried whether we would see an increase in femur fracture, heterotropic ossification, or hip and low back pain. However, we don't have any evidence from use of the subischial socket that these are common issues. How, unfortunately, current research evidence is too short-term to provide definitive insights regarding these types of issues. There is one case report that's a 6-month study of a bilateral amputee that suggests resolution of back pain when transitioning from ischial containment to subischial socket. While conducting our clinical trial comparing the ischial containment and new flexive sockets, we learned something about the issues. To potentially watch out for when transitioning patients to subischial sockets. In compliance with ethical committee requirements, we recorded adverse events with both sockets over 7 weeks. It's important to note that this was a non-systematic evaluation, as assessment of adverse events was not a formal goal of the study. In our study, no serious adverse events occurred. All the events that occurred were anticipated, as they are common issues generally encountered with any socket. As you can see, the adverse events we observed occurred in both sockets. What we've learned about transitioning patients between socket designs is the patient's motivation to change, the big factor for success. If they've always wanted a lower socket, then they will probably like the subischial socket design, despite the fact that it is still a socket with all its incumbent issues. Current research suggests that it should be more comfortable without a substantial change in function. The subischial socket can unmask weakness in the hip and core muscles. Hence, very weak patients may struggle to walk in the socket. If motivated, walking in the socket will, in and of itself, improve strength. However, targeted physical therapy can also help. The issue of muscle strength changes over time when transitioning from initial containment to a subischial socket is the focus of our current pilot study. If a patient has never worn a liner, you should anticipate the limb volume will shrink and that the patient may experience some form of transient skin reaction, including itching, redness, blisters, and sores. Sometimes this goes away on its own as the limb acclimates to being in a liner. Sometimes it requires a change of liner, and sometimes it is the socket issue that needs to be addressed. Thank you very much for your attention today. Here is a list of our publications about our subischial socket technique. And here are other references I cited during the presentation. Again, thank you very much for your attention.
Thank you. But at the moment we need to switch on to the next speaker. So Andy, if you are online, can you double check you are online and you can share your screen?
Hello.
Yes.
Let's see here.
Hello, Andy.
It works.
Yes. We can see your desktop and your presentation, and your audio is good. Excellent.
Good. Very good.
Yes, thank you.
All right, let's start here. Yeah, thank you so much for the invitation to be here virtually. Sorry I couldn't be there in person, but it's a great honor to be asked to present at your event, and very exciting to be celebrating 60 years. So congratulations. My name is Andrew Hanson. I'm a director of the Minneapolis Adaptive Design and Engineering Program here in Minneapolis, Minnesota, in the USA. And I'm also a professor of rehab science and biomedical engineering at the University of Minnesota. So first, I'll acknowledge the funding for the work we do. Most of our funding comes from the Department of Veterans Affairs, as well as the Department of Defense, but several of the projects I'm going to show today were also funded by other agencies shown here. This is a picture of our building where I'm at right now in Minneapolis. We are close to the Mississippi River, which is one of the largest rivers in the United States. In Minnesota, where it starts, is quite small. As you get to the south of the US, it gets quite large, but you can see a bit of it back here. We have a lot of things happening in terms of clinical rehabilitation here. We have one of 7 regional amputation centers, which are the highest tier of care for veterans with amputations. We're one of 5 polytrauma rehab centers, one of 25 spinal cord injuries and disorders centers, and one of 20 geriatric research, education, and clinical centers. So there's a lot going on clinically in rehab, and we've been growing the research in rehabilitation over the last decade or so. So our program started in 2010 with myself and Dr. Goldish, who's a rehab physician, now retired. But our program now has grown to close to 30 people, and very interdisciplinary group, many engineers, many clinicians, physicians, psychologists, prosthetists, orthotists, and therapists. So very, very good group that we've been able to put together. So the mission of the MADE program is really to develop and disseminate adaptive technologies and interventions that help veterans maximize their participation in meaningful activities. So really participation is what it's all about in rehab. You know, can people do the things they want to do? I think Michael's example of the fly fishing is a beautiful example of this. How do we get people back to what they want to be doing in life and the things that are meaningful to them? So it was a really, really nice presentation. So we think in order to maximize meaningful participation, we want to work to maximize functional abilities, but also prevent or mitigate complications of disabilities. So almost all of our projects fit in these areas. And my advisor, Dudley Childress, really loved this comic strip, I guess, and I think it's a good thing to try to emulate. So never trying to go too high tech or too low tech, but trying to find that right tech. And usually that's the lowest tech that gets the job done, in my opinion. So today I'll talk about some success stories from our group. We're working on a couple of different lower limb prostheses, a standing wheelchair design, and a skin screening camera system that will be hitting the market very soon. So the first system I want to talk about is a slope adaptive ankle foot system. And so this is trying to address problems where most prostheses really don't adapt to slope terrain. There are some that try to adapt. A lot of these use damping control, which takes energy out of the system. Many of them have sensors that have to try to sense if we're on a different terrain. And that usually causes a delay in trying to adapt to some different terrain. And most prostheses don't provide plantar flexion in late stance phase. So we came at this many years ago, just looking at what is the sort of biomimetic ankle function look like. So from many data collected during my PhD work at Northwestern, we collected torque angle data for the ankle. And this is the curve that we kind of see at the normal walking speed of 1.2 to 1.6 meters per second. And we looked at it and said this could be achieved with a system having two stiffnesses, a low stiffness early in stance phase, and then a higher stiffness after foot flat, where you could load and then unload along that same stiffness. And so this is the easy part, sort of drawing this idea and how it might work. This thing is sort of switching on and off this spring. And then the last 20 years have been the hard part. So this was done maybe 2003, so not quite 20 years, but getting close. I think what's most interesting about this approach of control is that if you set this at foot flat, you'll automatically adapt to different slopes because the foot goes further, the ankle moves further on a downhill slope compared to level or uphill. And so you can kind of see that this is adapting, it's setting a different equilibrium point for the ankle. So that was exciting, and something we wanted to try to achieve, if possible, with just purely mechanical systems. This is maybe the third, fourth, fifth prototype of different things we tried. I think this is the first thing that would kind of do this all by itself without anybody pulling a string or doing any crazy things. But it uses a weight activated cam clutch system. So it allows the foot to find the surface. The clutch then locks this ankle to dorsiflexion, can store energy in the forefoot and get that back at toe off. And then this weight activated part releases that clutch so that it can pick itself up for swing phase. So it doesn't remain plantar flexed when you try to go into swing phase. We were able to build this and test it, and you can sort of see it running here in slow motion. You can see how it sort of finds the surface, stores energy, and gives it back. And then at toe off, you can see how it picks itself up for the next step. And what people said to us is much more comfortable on slopes compared to prostheses that are not adapting, and took less effort to walk on the slopes. We also did some gait analyses on the instrumented treadmill. It's very, you don't get great forces except for during single support. So this is sort of just showing you single support data, but you can see the torque angle relationship shifting to dorsiflexion for uphill slopes and toward plantar flexion for downhill slopes. Whereas the usual prosthesis doesn't adapt, it doesn't realign for the slope. And this is showing just ankle angle as a percent of gait cycle. And another interesting thing here is that because of the way it functions, it does give you some late stance plantar flexion here. This is the level function in black, and then it picks itself up for swing phase, as you see here. So the big issue with this system is that when it released, it made this nice, not so nice, snapping noise, right? And I don't think we find too many people that like that noise every time they step on the prosthesis. So that became a very tricky thing, but this got us to the point where we thought this was quite meaningful and useful. Since that time, we've been working on other designs that are using more hydraulic slope adaptive systems. So instead of doing this with these other mechanical cam clutch sort of systems, we're now using kind of hydraulic circuits mainly to just lock and unlock this system. So this shows sort of the hydraulic circuit, and really the secret sauce is how this little red box lets the fluid flow at toe off. And so this was not fully figured out here, of course, but I'm happy to say we're now getting very close to this. There are systems that work completely with mechanical function only. The design is licensed now to Philauer, and we're working with Philauer to study this device. And in this past year, we had 6 people use it. Many of them said they would probably skip the last visit, so they would not have to give it back to us. And some said, you know, if it had an issue, they waited for this ankle to be fixed so that they could mow their lawn, because it's much more comfortable and they felt more stable. So we definitely think there's something to this automatic adaptation to slopes, and we're quite excited to continue working with Philauer and motion control and see this come onto the market. Another system we've been working on, I call ankle feet prosthesis, which looks like a misspelling, but it's actually, as you'll see, really the idea of it is a modular system with one ankle and several feet. And why would we do that? The reason to do it would be that you could allow people to wear nearly any footwear they want to wear. As many of you know, most prostheses are set up for one heel height shoe. If you try to take this prosthesis and use the low heel shoe, the alignment is way off and it's completely unstable. And similarly, if you try to go to a heel height that's too tall. And yeah, we know heel height's very, very important to the prosthesis alignment. And so how do neurotypical able-bodied women do this? Primarily, they change the ankle motion for different shoe heel heights. But notice too, the shape of their foot is different in each of these shoes as well. Knee and hip motions don't do as much. So if we were to design something, if we could address the needed change in the ankle and the foot shape, we should be able to create something that's biomimetic. There are a few systems out there. I think all of them come from this. Total Concept, I believe, was the first one to sort of do this, where you have a button, you can change the alignment, and you can adapt between 0 and 2 inch heels. However, this foot shape doesn't change, right? So This is probably why you can't go too much higher with different shoe heel heights. And it's probably designed, optimized for one heel height, honestly. The last thing is you have this process of alignment, which we, prosthetists feel is quite important, and it is very important. And they do all this in the clinic, get it optimized, but then they hand off this alignment task to the user. And some users can probably do it quite well, but there's several of these. This is a little outdated. The Oser one is a different design now, but basically they all sort of have that same approach. And really, this shown at the extreme, this is what happens if you don't change the foot shape and try to put this into a really high shoe. And this was a group of students in the US that were trying to do something useful, but I think they created this ankle design, but I think what was missing is really making the foot shape match the heel. One prosthetist and probably several others have tried this as well, right? Where they try to create these interchangeable feet. Art Price wrote about this back in 1991. He created a basswood shim on top of one foot to really address the alignment, but also to get the build height the same between these two feet and allowing people to switch their shoes. And one patient wrote, "Can't tell you what this means. It's truly liberating, right? It's really increased self-confidence." And the second person said, "She's walking more, she's doing more. She's participating, she's getting out there, and she's getting in better shape." And so these sort of things that, aesthetics maybe would think aren't super important are actually very important. And so I worked with Margaret Meyer on this project. We tried to create very inexpensive prosthetic feet made out of plastic and following kind of the shape and roll design. And we created these feet between heel heights of 0 to 7 centimeters. We used a flexible keel design, and you could interchange the feet. So it's similar to Art Price's approach, but basically come up with a way to very simply switch. And Margaret tested this in 3 women in Scotland who really appreciated the ability to do this. The one thing I would say is many high-heeled shoes have very stiff keels. So this one is made out of wood. So if you're trying to get the function in this 4-foot heel, it really wasn't happening, to be honest. So this is showing kind of the rollover shape. You see kind of the ground reaction force is staying here on the heel, and then sort of quickly running here. So this sort of indicates a pretty flat spot in this system. So, and I think the issue with this system, it still comes down to molds, right? So it's all about molds. If you want to create feet right now, most feet are made in molds. The cosmesis has to be made in molds. That means every size, rights, lefts. If you want one that looks more feminine, one that's more masculine, if you have different foot widths, molds, hundreds of molds would be needed. And there's a lot of expense when it comes to molds. So our approach is really trying to break the mold. Okay, forget the mold. And this is where I think 3D printing can make a lot of sense. So this shows kind of the concept. In this case, a woman veteran brings shoes to the clinic that she wants to use. The prosthetist takes some key measurements of these shoes, not too many, but the heel height is, of course, one very important piece. And they then send this to a 3D printer, or you send this to a company that 3D prints these feet, and you get an ankle and several feet. And then you can basically go between these for the different footwear you want to use. And so this was an early prototype that we created. A key to this is creating an ankle joint that's quite small, that can fit down inside these different feet. And so this is showing sort of how this ankle drops in. We're going to try to do this without any tools if possible, but there's really no alignment needed by the user. You just drop the ankle in, and the alignment's built in to the foot shape and the ankle bias in the design of the 3D printed foot. The current design uses a wiper approach, so it's basically a single axis sort of design where there are bumpers on either side of this wiper, but this allows you to make it quite compact and allows a good amount of dorsiflexion and plantar flexion. And then this really sort of shows the idea of it. I'm walking in this low-heeled shoe and I want to move to the high-heeled shoe. I can just take the prosthesis with the ankle out and drop it into the next design and go. So one key to success of all this is creating a digital foot model, right? So how do you create these three-dimensional shapes? And our engineer, Eric Nickel, really did a lot of important work here in creating a fully parametric three-dimensional model in SolidWorks that takes only two inputs and then designs a foot to be 3D printed. And this is Nicole Walker. She's a graduate student as well as a research prosthetist in our group, showing that these are very strong and people can walk on these with no issues. I'm happy to report we've licensed this to Unique, and to develop this commercially, we're working with Unique right now. If you don't know, but you may not know, but Unique specializes in 3D printing of prosthetics, and we're working closely with them, hopefully to see this in the market next year. Now I'll talk briefly about a standing wheelchair idea. When I first moved here, I met Dr. Goldish. He's a spinal cord injury physician, and he said there's many ways it's very good for people with spinal cord injuries to stand. Probably one of the best things is relieving pressure on the sitting tissues. As you know, pressure injuries are a very big problem. But also standing allows you to greatly improve your reach and what you can do. So there are several things out there. Standing frames, most are you stand, but you can only stay in one spot. This one you could be pushed around. This one you could move yourself, but it's very inefficient to get anywhere. There are standing wheelchairs, some that are powered, and these can stand and you can move both in sitting and standing. And so quite neat devices, but many people who have arm strength and the ability to use a manual chair don't necessarily want to go to a powered chair. It adds complexity in moving this system around. It's heavy, it's expensive. So there are manual wheelchairs where you can stand, but once you stand, you can't go anywhere. So our group worked on what we call a mobile manual standing wheelchair, and really the key feature here is the mobility and standing. So this is our first generation prototype. It uses you have to remove the push rim from the drive wheel basically, and there's a 2-chain system that it uses. So people can move around in sitting. They can go to standing. And then they can be mobile while standing as well. So this was initial work we did on this, was funded by Paralyzed Veterans of America. And we showed it to several veterans who were very excited about it. But some of the main things they said is little too wide. It's going to be quite heavy. We need to make this thing lighter. So we also, throughout this, we were very concerned also about stability. So we could do tests on an instrumented system here to really see where is the center of pressure of the ground reaction force and how that relates to the base support. And you can see that even in as far as I could lean in different directions, still well within the basis support. And then this is Eric's approach at testing the stability, which also shows quite stiff. Of course, we would recommend use of a chest strap for persons with spinal cord injury, but this is just kind of showing how stable the design is. We think this could be quite important. It may increase time in standing, relieving pressure on sitting tissues. It allows people to reach more items off the shelf, including at the grocery store, and can do other things. So there was a news event where one of our veterans was shooting baskets, and also this guy, when he first stood up in one of these chairs, he just rolled right up in my face, just got real close to me, and sort of scared me a little bit. And I said, "What did I do? Did I upset you?" And he said, "No, I just haven't been able to do that for a long time. Felt good to try to intimidate someone." So he's an athlete, you know, very skilled athlete before his accident. With some VA funding, we worked on the next generation of this. This version is much lighter, more compact, and we're working on a journal article to publish this now. But this shows the going from sitting to standing. Our next version of this will use a powered sit to stand, but a manual driving system, because you can see that's a little bit difficult. But this shows him moving around. And this sort of shows some of the utility, right? Grabbing something off the top shelf, handing it to Steve here, who did a lot of the making on this. And then the system can go back down to seated use, and you can move out from there. So we learned some things. We had 3 veterans come and try this, and we looked primarily at the mobility speed. Okay, so it's during a 100-meter roll test, which is part of the wheelchair skills test. And we looked at how fast did they go, what's the average speed, but also how many pushes does it take, right? And so one thing is you never probably ever get close to their ultralight wheelchair, which has no mechanisms for standing. And these are very, very efficient. And so you can see the speed's quite high, but our system during seated was about here, 1.1 meters per second. During standing, a little bit less, but to give you an idea of how fast that is compared to exoskeletons, in a review of exoskeletons and mobility speed, it's quite a bit higher than an exoskeleton. So what we'd like to do is get closer to neurotypical walking speeds. So one thing we noticed, and you may have seen it in the early video, is that during movement, some of these chains started to get loose, and that's because there's a lot of force, and it sort of tries to bring the sprockets together, and the chains get a little loose, so there's some compliance in the system. We added some compression members to really get rid of that, and we were able to improve the speed quite a bit, both in seated use and in standing use. And you can see for this person that came back to try it again, is getting very close to able-bodied speeds. So this system is now being licensed to Levo, and we're working on transferring that to their company. And then we have a new multi-site randomized control trial starting up that's going to compare mobile and standing to non-mobile and standing wheelchairs. Lastly, I want to show you a system we're very proud of as well, called the Skin Sight, or now it's being commercialized as the Habit Camera. And the idea of this is that for many people who are at risk of skin breakdown, we give them a long-handled mirror. But honestly, they don't work well for someone, particularly with spinal cord injury. It's very hard to see the areas you're interested in looking at. And so one of our physicians, Dr. Goldish, had this idea of, we'd really like to have a monitor separated from a camera and be able to move the camera where you want to put it. And so we've worked on this. This is showing a wired version of it, and it's showing a veteran doing some skin screening of his remaining foot who has an amputation on the other side. And this has been licensed to a company in California owned by a veteran, which is quite exciting. And the first pre-commercial release versions are being tested right now by a nurse scientist in our group, both with veterans with SCI and veterans with diabetes. And if I can pull this, see if this will work. To learn more about this, you can go to habit.camera, and this is sort of showing what the system is moving toward. It'll be more of a wireless system, able to help do skin screening. The other nice thing about doing it this way is if you take a picture, you'd be able to send it to your clinician, or your clinician could ask you for a picture. Please take a picture of your wound and send it to me. I want to look at it without having to come in. So it allows the person the ability to do that independently. So that's my presentation. I thank you very much for the opportunity to talk, and would answer any questions if you have them. Thank you.
And I think everyone here was very pleased and amazed by the work you're doing with the VA, because you show how simple can be effective, and it's not a contradiction. You can be simple and effective and very patient-centered. So it's a very neat examples of design and development for the benefit of your patients. So really, really impressed.
Thank you. And that's a big honor to hear from you. Thank you.
No, it's absolutely honest opinion. I don't know if there are other questions from the audience. I think we are all very happy with this session. We have to apologize with staff. There were technical issues with the audio. We will try to make sure that all the information are conveyed to all the audience in other ways. And I have to thank again all the speakers. I think we had a very interesting and informative session about what's going on around the world with friends that improved our knowledge about patient-centered research. So with any further delay, thank you very much. We can close this session, and thank you for participating. Thank you.